Video we're going to look at converting from polar complex form into Cartesian complex form, and that's what we got there. So we have a question. It states convert the polar complex number 4.2 and minus 68.2 degrees to Cartesian complex. So we're familiar that we have our polar form of a complex number, and we're going to look at converting that to the standard Cartesian complex that we're maybe a little bit more familiar with. So you see over here on the left, I've got our very important Argand diagram that we use to plot complex numbers. We have a real axis in the position of the x-axis, positive to the right, positive to the top, and we have our imaginary j-axis that runs vertical, and we have our origin in there. So the first thing we do is, which is going to be very helpful and going to get us a lot of marks in our test, is we're going to plot this Argand diagram and then try and plot the point, because the point, plotting it keeps us right and it allows us to visualize it a bit better and ultimately check our answer to make sure we're along the right lines. So if I'm going to plot this, I know I'm going to have a modulus length of a phasor at 4.2, or the hypotenuse of my triangle that I create will be 4.2, and I have an angle of minus 68.2 from the x-axis, from the real axis. So I'll give it a point here, right? We're sketching this roughly. So I'm going to sketch that point in there, and then I'm going to draw in my phasor. Okay? So I've done that. And then from that, and I'll just try and keep it in some different colors here, I'm going to generate my right angle triangle. You see there it is there. And we always try and aim to make a right angle triangle with the positive, with the real axis. Okay? We know from some of our rules that if we're swinging this way with the angle, it's going to be a positive angle, and if we're swinging this way with the angle, it's going to be a negative angle. So that's where this here is coming in, this negative angle. We know the angle's not greater than 90 degrees, so it shouldn't be verging into this side of the Argand diagram. So we have it here quite nicely, looks right. Okay, and we also have what's known as OR, the length of our phasor, fitted in there. So that we've set it up right, it looks right for us. So now let's start trying to calculate some points. Well, we know this side here of a right angle triangle is going to be represented by y, and we know along here this length is going to be x. We have our nice little right angle in there. So how do we find that? Well, we can set it up with all our very important rules of right angle triangles. We know the hypotenuse, which is OR, will equal the square root of x squared plus y squared, and we know SOC, TOA, two very important rules when we're dealing with right angle triangles. Okay, the one that's going to be really important to us here is sine, because we'll be told that sine of theta equals our opposite. The opposite is y over the hypotenuse, which we know is OR, and cos is also going to be very important to us, because we've cos theta equals the adjacent, which is x over OR. Now if you can't remember SOC and TOA, and then tan is opposite over adjacent, you can remember the little rhyme, silly old Hitler couldn't advance his troops over America. So when we have this, right, well, let's see what we got. Well, we know what theta is, because we know this is theta, and we know what OR is. This is OR. Okay, so we can use these two, we can rearrange these formulas, manipulate them a little bit, to find the values for, indeed, x and y. And we're just running out of time in this video, so we're going to look at it in the next video.